Well, first of all, thank you all for being here. Today, at the same time, we have lots of sessions that are probably, at least to me, more interesting than this. So I'm so glad you guys decided to be here with me. I'm Monica Beckwith, and I'm going to talk about garbage first, garbage collector with examples this time. For people that know garbage first, garbage collector, they may also know that it's going to be the default collector. So for example, when you run Java up until JDK8, you get parallel GC as your default collector, right? You have to set CMS or G1 GC explicitly on the command line. So with Java 9, you get G1 GC as your default collector. Java 9 also has unified logging, GC logging, but most of the logs that I've shown here are, I don't know if I have any logs here, but most of the work that I've shown here is with JDK8. So the logs will be different, but the output or the data from those logs would be similar. The logs, the call to the logs, the invocation command may be different, actually are different. Okay, so with that information, let's get started. So I'm a performance engineer. I used to work for AMD, and then I worked for Sun, and then Oracle eventually. The last job title I had at Oracle was G1 GC Performance Lead. Now I'm a consultant, and I work for myself at concurrent LLC. And I'm also a partner at Extreme Performance Experts. This is we offer training courses. It's me and Kirk Pepperdine. We offer training courses for people interested in performance, Java performance. Okay, with that, let's move on. What I'm going to cover today, I'm going to talk about G1 GC. It's going to be kind of fast-paced. I'm going to introduce certain concepts that are really important in tuning garbage first, garbage collector. So I'm going to talk about the heap regions, what are humongous regions and what are regular regions, and then our humongous objects, basically. And then I'll talk about some additional structures and kind of like something that adds to footprint of G1 GC. And then GC phases. Basically, G1 GC goes through young collections, and then after the threshold is crossed, it starts a concurrent mark cycle, and then eventually, after you've identified the candidate all regions, you go and do mixed collections. The identification of candidate all regions is basically just how expensive the regions are. So basically, it'll be arranged from least expensive to most expensive. And during every mixed collection, you select a couple of candidate all regions till you exhaust your list or till the cutoff is reached, which are basically tunables in G1 GC, and we'll talk about that as well. And then we'll get into details. As a performance person, this is where I want to concentrate more on, and I have a lot of slides in there. So we'll talk about tuning considerations with garbage first, garbage collector. The first and foremost, we want to talk about mixed collections. Like I said, there are lots of tunables, and I want you to understand why we need certain tunables and in what cases we would want them. Next, I'll talk about components of a G1 GC pause. So when we talk about GC logging with G1 GC, when you do print GC details, you get a lot of information. So I will kind of quickly try to get you guys familiarized with that information. Then we'll talk about humongous objects with G1 GC, and then fragmentation in G1 GC, evacuation failures in G1 GC, and finally allocation rate and promotion rate, which has nothing to do just with G1 GC. It's with any garbage collector. You have to, especially with hotspot garbage collectors, you have to be aware of your allocation rates and promotion rates and how you're sizing your heap. So I wanted to talk about that as well. So let's get started with G1 GC background. Of course, the main thing about G1 GC is regionalized heap. What is regionalized heap? So everybody knows this, hopefully. This is your traditional Java heap. You have the contiguous Java heap, and then it's divided into young generation and old generation. Young generation further has Eden space and survivor space, and survivors are called to and from, or S0 and S1, okay? Most allocations happen in Eden, and then after, as Eden gets full, and you cannot allocate anymore, so allocation failure will lead to a young collection, and that would, all the surviving objects, which means the live objects, are moved to either of the survivor spaces. After the objects are aged in the survivor spaces, they are promoted or tenured to the old generation, okay? With G1, the same contiguous Java heap looks something like this. It's the heap in G1 is divided into similar sized regions. The size of the region could be anywhere from 1 meg to 32 megs. It's a power of 2. Excuse me. And they are, like I said, similar size. There's no variability in size. And at any given time, either you have free regions or you have occupied regions. Okay? So as you can see here, we have the ones that are not gray are free, and then the gray ones are occupied. Out of those occupied regions, you could, either of those regions could be either young or old or humongous, okay? So young regions are basically where your young objects live, okay? So they are basically Eden and survivor spaces. That's what comprises the young regions. The old are where your promoted objects live. And humongous regions are where your humongous objects live. And we'll talk more about humongous objects soon. So in the same the bland graph, or the drawing earlier, I put some color in. So this is just for explanation purposes. You see we have 2 Edens. Sorry, I'll just keep walking. So we have 2 Edens, 1 survivor. There's a contiguous humongous region right there at the bottom. And then we have 3 old regions. So like I said, at any given time, your occupied regions could be any of from any generation, so to speak. So let's talk about humongous objects. So in this, the notation in the, henceforth is young generation is in blue or turquoise, and old generation is in green, or whatever, closest to green. And I have 3 objects. So object number 1 is less than 50% of G1 region size, okay? Object number 2 is greater than or equal to 50% of G1 region size. And object number 3 is greater than a total region. It's greater, is beyond, will fit beyond a region. So how would G1 allocate those regions? Objects, sorry, into the regions. The first one is less than 50% of the region size, so it's considered a normal object and will follow the normal allocation path, which is into the TLABs, fast path allocation. That is thread local allocation buffers, so they'll be allocating the object, the normal objects, into the Eden space. The second object is greater than or equal to 50% of G1 region size, so it'll be allocated out of the old generation into something known as humongous region. So humongous objects are allocated directly into the old generation. And the third one is greater than G1 region size itself, so it'll need 2 contiguous regions. Again, it is out of the old generation. They are still called humongous regions, but they're contiguous, okay? And we'll see examples as we go along. So what we've seen, the first one is not humongous, so it follows regular allocation it'll be allocated into the Eden space. The next 2 are humongous, and in fact, the third one actually needs contiguous regions to be able to fit. So G1 will need contiguous regions in the old generation to be able to fit that object. Okay? So let's talk about the footprint overhead in G1. The first thing that G1 needs is something called collection set. Collection set is basically a set of regions. So for young collection, it incorporates all the young regions. Basically, generational hotspot collectors collect the young generation in its entirety, not just G1 GC, but also the throughput collector, CMS collector, and even serial GC. The young generation is collected in its entirety. So when you see a young collection in G1 GC, you have to know that the collection set will incorporate all the young regions, okay? And mixed collection set, and mixed collection, the concept of mixed collection is something that's new to G1 GC. So if you compare it to any other garbage collector, so you know the throughput collector, you know the CMS collector, the throughput collector, when it has promotion failures, it does parallel collection, but it's a monolithic collection of the old generation. Actually, it's the collection of the entire heap. So there's a single stop the world pause that collects the entire heap in throughput collector. In CMS, you go do in-space deallocation till you have fragmentation and then concurrent mode failures, and eventually you have a fallback, single-threaded fallback GC, right? And again, that's monolithic. In G1 GC, in order to collect the old generation, the concept of incremental compaction is introduced. And incremental compaction is that you identify candidate old regions, and you only add so many regions based on the constraints and the tunables that you have to each collection that includes the old regions. So such a collection is called a mixed collection because it has all the young regions and a few candidate old regions. Hence, it's called a mixed collection. G1 GC is based on the principle of most garbage first, hence the name, garbage first. So the idea is to have the collections not be too expensive. If the collection is deemed expensive, then those regions, those old regions, will not be included in the collection set, okay? So for example, we use the same picture. We have those Eden regions and the survivor region. So as I said, young generation is collected in its entirety. So the collection set for young collection will have all the young regions. And during a mixed collection, again, the collection set for a mixed collection will have all the young regions and only a few old regions, as shown here. So although you see about 4 old regions, there's only 2 of them that have more garbage than the other 2. So only those 2 are included. And it's incremental, so that you'll see multiple mixed collection pauses. So there's a data structure called remembered sets, okay? It's used for maintaining and tracking incoming references, okay? It adds an overhead. So when you're comparing footprint between CMS and G1, you'll definitely see an additional overhead in footprint, and that's because of this. Okay, so if I'm a region, I have my own remembered set, and similarly, every other region has its own remembered set. The job of my remembered set is to know incoming reference to me, okay? That's all it does. Maintain and track incoming references to me. Because we collect, so the advantage of collecting the entire young generation is that we don't need to track those references, right? So the only 2 kinds of references we want to track are old to young references and old to old references. And then remembered sets have they become denser depending on how popular a region is. So if I am a region and I have one popular object, which means it's really everybody's trying to access it, then for that object, so my remembered set will get denser. If I'm a region, I have multiple popular objects, then again my remembered set is going to get denser. So based on the popularity of the region, the density of remembered sets will increase. And that's one of the reasons you may have performance degradation. This is a picture I just wanted to quickly Maybe I won't cover it, but this is from the book Java Performance Companion. And what you see here are some young regions and old regions. And what I'm showing here is that we don't keep a track of incoming references from the young region. So basically, if you see our set for region Y doesn't have anything because the only incoming reference is from a young region. Region Y is an old region. Incoming reference is from a young region. So we don't need to track it. So our set for region Y is empty. So that was just an example trying to explain what I just said earlier. All right, so moving on to G1, GC phases. I hope everybody can see the colors here, right? So that we have 5 different colors. Okay, if you need me to talk to about the colors, I can do that. But if you can all see it, then it's good. I'll just proceed. All right. So G1, GC starts with young collections, a bunch of young collections. And as the heap occupancy increases, we start the marking cycle. So at that white line, you see that the occupancy is equal to initiating heap occupancy %, which is also known as your marking threshold or marking initiation or all those things. I also call it IHOP. So after that, you start your concurrent marking cycle. The first phase, and I'll quickly list all the phases, but just here, there are a couple of stop the world phases in the concurrent cycle. The first one is initial mark. That's what you see in green. Initial mark is also piggybacked, which means it happens at the same time as young collection. And then you start root region scanning, which is concurrent. And during root region scanning, a young collection cannot interrupt the concurrent process of root region scanning. Okay? So after root region scanning is done, you have concurrent mark, the actual marking that happens. And by concurrent, I mean it happens at the same time as your application is running. So you have your application threads, and you have a few concurrent threads that are happening at the same time. It's not stop the world. Okay? So whatever you see here are stop the world pauses. That's why you see these discrete pauses. Okay? They're not concurrent. They are stop the world. That means only GC threads are working at that time. The application threads are not working. So after concurrent marking, concurrent marking can be interrupted by a young collection, and that's what you see here. There's a blue line right after the green line. So because that's a stop the world pause, and that's okay. You can have multiple of those. Eventually, you'll get to remark, which is stop the world again. Remark is also known as final marking. That's where you want to do so you may have missed some things during concurrent mark because your application was also running, so you're trying to catch up and make sure you marked everything. That's what happens during remark, and then there's cleanup pause, the small one. Cleanup is also concurrent, so there's partly stop the world, partly concurrent. And then you have just one young collection that determines how many mixed collections you're going to have. So after concurrent marking, we know the liveness of our old regions. We have sorted the old regions based on the most efficient collection, so based on their efficiency. So the least live ones, or the least expensive ones, will be collected first, and the most expensive will be later. So now we have, at the last young pause that you see, we know that we need to include so many old regions based on our targets, okay? So then you see the incremental collection, which is also known as mixed collection, or you can also call it incremental compaction. There are different ways, but it's the same thing. So we see 5 different mixed collections here. And during that, we're collecting these candidate regions. So we have different thresholds. Sometimes the thresholds, because it's not hard stop, so sometimes the thresholds are just there to let G1 know what it should do. But because of the prediction logic, it may blow your pause time target, and we'll talk about it in tuning. That's what you would see in G1 GC. These are all the stop the world pauses that you will notice in G1 GC. You could have more mixed collections because it's incremental, And then, so moving on from here, I'll quickly talk about what happens during a young collection. So basically describing what I just said. So all your Eden regions and survivor regions are collected, basically compacted, and the live objects are moved to either survivor or promoted based on their age. Then after you have a multiple of young collections, like I said, you have the marking initiation, known as IHOP, and it's based on the total heap size. It's an occupancy threshold, and that indicates to G1 that you have to start concurrent marking. There are two useful options, and I've clubbed conc GC threads here. So first of all, IHOP is adaptive in Java 9. Prior to then, it was the default is 45%. So, but it's tunable. You can use the IHOP option, and you can specify it based on your observations. And there's something called the conc GC threads. Remember when I said root region scanning and concurrent marking, they work concurrently with your application. Sometimes you may want to adjust this particular option to get through that concurrent phase faster. So, that's by default 1/4 of your parallel GC threads. So something to keep in mind. So concurrent marking stages, I already covered all of them. So one thing I wanted to highlight was that if you're using something prior to JDK 8, update 40, and you have issues with class unloading, then with JDK 8, update 40, class loading with concurrent marking is enabled by default. So that problem will go away, okay? And I've had many people that had that issue and then upgraded. If that's a major concern, then of course you should upgrade. Another thing, prior to JDK 8, update 40 again, humongous objects, the only way humongous objects could be reclaimed was during a cleanup phase. Now, during the cleanup phase, remember I was talking about the liveness of the old regions is determined. If at that time the cleanup phase finds that one old region or multiple old regions are empty because they are full of garbage, it can reclaim it. It doesn't have to wait till a mixed collection pause. So this was the way, if you had a dead humongous object, this was the only way, other than full collection, that humongous object would be reclaimed. So if you had any problem prior to JDK 8 update 40 with respect to humongous objects not being reclaimed, that has changed in JDK 8 update 40 and onwards. So with JDK 8 update 40, now humongous objects can be reclaimed during a young collection pause. Okay? It doesn't have to wait till a full GC or till a cleanup. Okay? So it's reclaimed here. Now coming to mixed collection, again, yes? Well, it's just treated as an object that is. So you can do those things because you know where you're allocating those humongous objects. So you have an idea where they are. So you can go and check their liveness too when you're doing marking. No, just during your young collection. You're already doing marking and all those things for your young too, right? So you can just include the humongous regions as well at that time. So those which are allocated in that. Yeah, because remember I said normal allocations are in young, and then humongous always go in old. So we already know that those are humongous. We already know it. Okay. Sorry. So this is what we had seen earlier, our collection set, remember? So we have all the young regions and a few old regions. And after a mixed collection, we have achieved compaction. So they're moved, all the live objects are moved according to their age and whatnot. And here you are, okay? So now, moving to tuning considerations with G1 GC. The first and foremost is taming mixed collections. So the reason I say taming mixed collection is basically you try to achieve where you want to be by tuning various knobs, right? So, so why do we need to tame mixed collections? So say you have your young collections are meeting your SLAs. So basically your system level agreements are met based on just the young collections alone, but the mixed collections are happening too frequently. So the GC overhead is increasing, and or your mixed collections are blowing your SLAs, basically the latency, so they're more expensive. So either too frequent or more expensive, okay? That's the reason why you'll tune your mixed collections. If everything is happy and going nicely, why would you bother, right? So there are two reasons, frequency and latency. So for example, here, you see all the collections are less than 100 milliseconds, except for the last one here, this one, right? So what do? So if just bringing it down is the only concern, then you can divide the expensive collection. You had only one expensive collection, right? So you can divide your expensive collection further into smaller, inexpensive collections, okay? So how do you know, first of all, what I need to do next, right? So there's an option called print adaptive size policy, and you'll have to go look at the log, all right? So there, and just what you're going to observe, I'm going to just visualize it over here. I'm not going to show you the log, because the last couple of times that I showed the logs, it was too much information, right? So in the amount of time that I have, I will just let you know a couple of things. So you have a minimum threshold for the old regions for each mixed collection, and then you have a maximum threshold. So minimum number of old regions to be included in the mixed collection set is tunable. Maximum number of old regions to be included in a mixed collection set is also tunable. So if you find something that's expensive, you can divide it further, so reduce your maximum down, right? You could do that. So the option for those two, so first one is governed by G1 mixed GC count target, and the second one is G1 old C set region threshold percent. So instead of saying mixed C set, it's saying old C set. It's the same thing, because basically it's controlling how many old regions are in your collection set. Simple, maximum threshold, all right? Now moving on. So that was because latency, one single pause was expensive. What if your GC is too frequent? Mixed collections are too frequent, right? So your GC overhead is the problem, okay? And you have enough heap, right? And I'll show you an example. Because you have enough heap and you know your humongous regions are not gonna blow your heap or whatever, so you have everything here, interesting. You can just remove the expensive regions from your collections. Keep them where they are. You don't need to include them in your collections at all. So how do you do that? So you just eliminate them. I'm saying that, if the 5% of my regions are expensive, I don't care about them. I have enough heap to spare. Leave them on the heap till they become less expensive. Simple. I don't want to move objects around if there's so much of live data in there or whatever. So there are two options. You could eliminate based on the liveness. Remember, after concurrent marking, we know the liveness per region. So we are our own bosses, right? We can eliminate based on the liveness per old region. The second thing you could do, you could also eliminate expensive old regions altogether, right? So the two options that let you do that, the first one where you can eliminate, the first one where you can eliminate based on liveness is called mixed GC, G1 mixed GC, live threshold percent. I think by default it's 85%, and you can lower it, you can increase it. The second option which just says that keep them in the heap, I don't really want to bother, is called G1 heap waste percent. I'm okay wasting my heap, it's simple as that. So I have enough heap, keep those expensive ones in the heap. By default it's 5, you could increase it to 10 or whatever, if you have enough heap to spare. So there are two ways, so frequency and latency, and there are 4 different options that we discussed, right? Now, components of a G1 GC pause, like a single stop the world pause, what is it made of? So we saw the phases, now we're going to dive into each pause. So I'll show you the pause, how it looks in the GC log, but something very pleasant now is what we see here, and I hope everybody can see it. If not, then please forward and have a look. These are, so basically a single GC pause has two phases, the parallel phase and the sequential phase. During the parallel phase, G1, GC, and actually other GCs too, they employ multiple parallel threads that do work stealing, they have work queues, and all the beautiful queuing theory optimizations, right? And then after the parallel phase is done, you have some sequential work that is done, which is like code root fix-up, and then clear card tables and other times, okay? So what we have done here is like, you'll probably, many you may have seen this earlier, I mean, somewhere else as well, it's basically just plot all the pauses. So here we see the pause time, the parallel time, and the object copy times are tracking pretty well, right? So what we saw there is an ideal situation, right? So what should be a major contributor to your pause? Because we're doing, it's a stop the world pause. What's the major work that we're doing during a pause? We're trying to move live objects. We're trying to achieve compaction by copying live objects. So what should be the major contributor of your pause? Ideally, you will see that most of your pause time should be spent in copying live objects. So object copy times should be the major contributor. If it's not object copy times, then you have a problem, okay? And let's see how. So it's the same graph. It's nice. Everything is tracking nicely. See, those are your object copy times in turquoise, which maybe you can't see, but you can just see it's very close to each other, to your pause times and your parallel times. So what happens when it's not the case? What would you see? You would see something like this, okay? So here, what you see is that the object copy time is kind of about 100 milliseconds. There's a 100 milliseconds difference in the parallel time and object copy time. And between the pause time and parallel time, you have about 50 milliseconds difference, okay? And that is because of that yellow line, which is update remembered sets. Remember I said remembered sets can pose issues during your pause based on the density and other things. So in this particular case, update remembered sets took about little less than 125 milliseconds. And the difference between the pause time and parallel time is 50 milliseconds, and that's because of the other times. So other times are where your reference processing and other things happen, okay? And I have seen in my consultancy work that lots of people have reference processing issues that they don't know because of the libraries they're using or whatever they're calling. And you can clearly visualize it here, right? Similarly over there, again, update RS, which is update RS time is the same as your pause time. It's expected to be 10% of your pause time. It's the same here as the object copy times, I mean. And then you have, again, the other time. You see, it's like 125. So we have some issues here, right? But this is how your GC log would look for that particular pause, the first pause that I showed, right? So you have the parallel time and all the work that is done during the parallel time. And then you have the sequential times, which are code root fix-up, code root migration, clear card table, and others. And there are various things that happen during the others, and only 4 of them are mentioned here. So in that particular case, when we saw the other time was 50 milliseconds, 34.6 milliseconds were because of reference processing. It's something nice to investigate further, right? Another thing that you have to be careful of, what you're plotting, what you're observing, right? And as a performance person, I always talk about what are you measuring? Measure your worst case, right? So in this particular case, you can get minimum, average, maximum, and of course a difference. So for this particular pause, the difference was 65 milliseconds, all right? So if I plotted just the maximum, which you saw earlier, you would see something like this. But if I plotted the average times, you see, the yellow line is pretty normal when you're plotting the average. There's another thing, measurement and measure and plotting what is important, right? I don't have much time to talk more about that because we're talking about G1, GC. But again, with G1, GC, make sure you're plotting the max, okay? Humongous object requirement. Okay. So ideally, humongous objects are few in number and are short-lived. Right. a lot of long-lived humongous objects can cause evacuation failures if you're not sizing your heap properly. If your old generation is not, if you don't know that humongous objects are directly occupying space out of your old generation, then you don't know that you need to increase that space, and you can get problems because of that. Because humongous regions add to the old generation occupancy, right? So we saw this earlier, right? In that particular case, what did we observe? We observed that they're allocated out of the old generation. They are not moved, right? Unless they're dead, and then they're reclaimed. But you don't move. They're not including in copying phase. If they're live, they're expensive to move. You don't want that to happen. Again, I already spoke about that. All right. What else did we observe? We observed this kind of space, which is wasted space. I'm sorry you cannot see the text in red. It says wasted space. Because each humongous region can only have, each or contiguous region can only house one humongous object, you have so much of wasted space, right? Again, so humongous objects can pose the following issues. You have wasted space, which can lead to fragmentation. And then you have evacuation failures because you don't have enough two-space regions, okay? So let's talk about fragmentation in G1. G1 has some internal fragmentation that we already had covered, so I'm going to go quickly through them. Remember I spoke about heap waste percent? I say that I have enough heap to spare, so I don't want to collect expensive regions, right? So G1 is designed to absorb some fragmentation. So it does have it. It's internal. You don't want to collect those regions. You don't want to touch those things. So its default is 5%, and it's because you want to leave those expensive regions out, not included in your collections. There's also, we spoke about the G1 mixed GC liveness threshold, right? That is when each region if it's more expensive than this threshold, it's not included in collections, right? So again, the default here is 85%. And again, the trade-off is so that that expensive region is not included in any collection. What about humongous objects? You have wasted space, right? That's internal fragmentation. But there's something called external fragmentation too. I'm not sure if I have that. OK, yes, I do. So it happens because you're trying to allocate humongous objects. And remember, the requirement to allocate humongous objects is contiguous regions. What if your whole old generation has free space, but it doesn't have contiguous regions? And that's fragmentation too, right? So that can, humongous objects can cause fragmentation if you're not sizing your heap accordingly. Oh my gosh, OK. So fragmentation can lead to evacuation failures. Now let's talk about evacuation failures and what other things can lead to evacuation failures. Evacuation failures are also known as promotion failures or two-space exhausted, multiple terminologies, but they mean the same thing. And you have those in CMS, and you have promotion failures in even throughput collector. That's how you get the old collection kicking in, right? Ah, goodness. Again, red. I'm sorry you cannot see the red, but the first text in red is two-space exhausted. And in the other time, you'll also see how much time that evacuation failure took. So in this particular case, it took 437.5 milliseconds. That's a GC log. You can see that when you enable print GC details, right? So I can see that during my young pause, I had an evacuation failure, and that evacuation failure took 437.5 milliseconds. I'm sorry about the red. So what is an evacuation failure? When there are no more regions available to be able to move your survived objects or your promoted objects, or within, like from old to old also. Simple. It's expensive, and the usual pattern is with the collectors that have evacuation failures is that it'll lead to a full collection, right? So you want to avoid it. A heavily tuned JVM command line could be restricting the G1 GC adaptability. GC ergonomics is a HotSpot JVM term. So I'm using the same thing. And adaptability. So G1 is adaptable. You give it a pastime goal, and I guess I say that. Start just with your heap sizes, and a reasonable pause time goal and see where it leads you, right? Your live data set and long-lived transient data may be too large for the old generation. So when people talk about live data set, they only think about the live data. What about your transients? You are promoting, after you age them, you are promoting those objects in the old generation. And these are your transient live data, right? So you have to accommodate them too. And then remember humongous objects too. So check your live data set plus everything else and increase the heap to accommodate that in your old generation. Your IHOP could be the issue. Again, if the threshold is too high, then guess what? Your marking cycle may not be able to complete in time, and it can delay the incremental compaction, which is mixed collections, and then you can have evacuation failures, right? Marking cycle could be taking too long to complete. Remember I said we have marking threads that help with the marking cycle, right? So increase those thread counts, and reduce the IHOP to start marking cycle a little bit earlier. Two space survivors are the problem, which means that you notice that you have enough space in the old generation, but your survivor space is the problem. So there's something, oops, sorry. There's something called G1 reserve %, and basically it's a false ceiling. I think the default is 10%. You can increase it up to 50%, which means that it'll allow the region to accommodate more survivors, basically, simple. Evacuation failures. Oh, goodness, I'm sorry. What did I do? So let's go quickly. I did something crazy. Okay, so now here's a really, it's JBB 2005 run on my laptop, and I tried to just push too many command line options just to give you an example of how crazy you can get. And this is what I see. I have warehouses running. I have too many threads than my laptop can handle, and I have all sorts of problems. And I have tried to restrain my young generation size, like minimum. I gave it a, like, don't have the young generation below, so new size. I specified new size, and my heap is only one gig. And you have lots of, this is your occupancy information, all right? What that ended up doing was I had multiple evacuation failures and full garbage collection, and it just went on, and it's crazy. You see how the yellow line basically blends in with your heap, the total heap size? That's your old generation occupancy. It just keeps increasing, and the concurrent cycles are not able to keep up. We don't have enough threads, all craziness, all right? Then I said, okay, let's take step one. Remove the nursery constraint. Keep the heap at 1 gig. Remove the nursery constraint. Let G1 do its magic. Yes, it's kind of a lot better, right? Right. We see that the old generation is not reaching, having the issues, and the heap occupancy is before and after getting up better. Still have a lot of evacuation failures. So I went and I opened that in GC Histo, and what I see is that I see my initial mark cycle, and I don't see any other things. So my concurrent cycles are having issues, and I see that I have full collections right after the two-space exhausted, because two-space exhausted couldn't do much work too. And then I also see a bunch of messages in print adaptive size policy output for the same section. What I see are, oh gosh, I'm sorry again, red. I see that did not expand the heap, reason heap already fully expanded, and recent GC overhead higher than threshold after GC. So it's telling me it was trying, and this is not the first time I see this message. I see this message all over my log. It's trying to expand the heap, but it cannot. And my GC overhead, basically if the frequency of my garbage collection pauses, are way above my threshold. So I had enough heap to spare, like I said, remember, and I increased it to 4 gig. I have a lot more. And then everything was okay. This is simple spec JBB 2005. It's got very few, each warehouse has about 32 megs or something. So it's not really intensive workload. But since I had constrained it so much, I had constrained my command line so much that it was not able to breathe. G1GC was not able to breathe. And here, actually, G1GC managed to avoid mixed collections altogether because it can just manage all young collections, and it's a beautiful graph right here. I can tune it further, but I just wanted to show you an example that don't constrain a command line. All right, finally, allocation and promotion rates. Very important to track them. This is an example, and if you have seen my other presentations, you may have seen it before as well. This was an application that was running on CMS, and it would have these allocation spikes. And because they had already tuned CMS so much, but the sizing was not, the tuning was not done to accommodate the allocation spikes. And what you see is the promotion rate increases just as the allocation increases as well. But because, and this is when I plotted that CMS heap, what you saw that, the yellow lines are not visible. I'm sorry. Can everybody see the yellow occupancy line? So that's the old generation occupancy. You see it's already around 13 gigs, right? And the total heap is 16 gigs. So right when the allocation spike happens, which is, where's my pointer? Well, anyway, so just right here, all the way up there, your heap occupancy before GC and old generation occupancy are basically meeting, which means that right there you have a promotion failure. Then right next to it you have a concurrent mode failure, and then you have full GC. And you see how the occupancy drops. So you have enough room in the old generation, but because of fragmentation issues and all those things, your occupancy drops only after full collection. So if you're not tracking your allocation rates and promotion rates with garbage collectors, you could have a problem. Because of the way G1 does incremental compaction, this problem was not seen in G1. It wasn't that bad, but we could tune it further. And that's all I have. Yay, okay. If you have any questions, we can take them outside.